All right, so today we have Mitch Weaver who will tell us how to read between the special Kahler structures of N equals 4 super-Yang-Mills theories. Take it away.
Awesome. Yeah, thank you, Julius, and thanks for letting me come talk about our riveting work. It's good to give something back to the Quiver meetings, given how much I benefit from them, watching them and whatnot. So this is going to be on based off of a paper that came out near the beginning of October with Philip Argyris, Antoine, none other than Julius himself, and Matteo Latito. Yeah, and it's going to be sort of explaining a story that takes into account um, something called special Kahler structure of 40 n equals 2 Coulomb branch geometries. And our specific setting is going to be in the realm of n equals 4 super-Yang-Mills. And ultimately, what we end up going about doing is serves as sort of a low energy test of S-duality. So hopefully, in the process of going through the talk, it'll become apparent why I have this kind of subtitle there. But with that, let me get going. And yeah, please feel free to interrupt me at any time with any questions or anything to make this sort of as lively as possible. It's kind of dinner time here, so I could use a little a little interaction after a long day. Um, yeah, so starting with some motivations here, I'd say our central question is the following. We're trying to identify what field theory data of a 40 n equals 2 SCFT encodes this so-called special Kahler structure that defines the Coulomb branch geometry. This is kind of our kind of like long vision, the thing that we're sort of chasing here. Um, and so just really quick, I want to just remind you of some of the basic aspects of the Coulomb branch and its geometry. So it's believed to be a universal component for um, all interacting n equals 2 superconformal field theories, at least conjecturally. And it has a couple geometric components. So it's a so-called Lagrangian fibration, and this fibration has a base, which is a singular space or an algebraic variety. Um, and it has a fiber, which is a special type of complex torus, which is called a polarized abelian variety. And this kind of geometric data is subject to uh, these so-called special Kahler integrability conditions. And sort of in more physics terms, the base here is what parameterizes the vevs of um, the massless scalars in the vector multiplet. And it's the target space for a nonlinear sigma model describing the kind of the low energy effective action that governs the physics here of these scalars getting vevs. The torus fibers, they parameterize the couplings and charges between 4D pure Maxwell theory, the gauge fields of these vector multiplets, the U1 gauge fields, and the massive kind of BPS states. And these couplings typically depend on the value of the VEV, by which I mean like where you're actually at in the moduli space. And finally, this special Kahler structure is really what ties these latter two components of the fibration together in a way that's kind of all compatible with n equals 2 SUSY. So that's the idea. And we'll go over this in a little more detail here after I get through this motivational slash introductory part. So okay, I want to continue kind of reviewing a couple key ingredients here. So something we've come to understand in the past, I don't know, a little more than a decade or so, is that a quantum field theory has two types of data associated to it, and we can categorize these as local and global data, respectively, where this local data is really what determines the correlation functions of local operators. And it's at least in a conformal setting, it's completely specified by your spectrum of local operators and their OPE algebra. And then we also have this so-called global data, which is the additional data, kind of very in somewhat general terms, the additional data you need to specify the theory on an arbitrary compact manifold without boundary. And when you provide such data, we call this an absolute theory. And there can be kind of distinct sets of global data or absolute versions of a given theory with the same local data. And for each kind of consistent pair of local and global data, you call that a global variant of the SCFT or QFT more generally. At least that's the language I'm going to use here. Okay, so for these 40 n equals 2 SCFTs, we know that the local data encodes already part of the Coulomb branch geometry, and in particular, it encodes the chiral operators, which are the ones getting vevs on the Coulomb branch, and their OPE algebra, which define the coordinate ring of the Coulomb branch as an algebraic variety. But in general, this local data really misses this additional kind of vibration structure that defines and is tied together by this special Kahler structure. So a natural question is, what is the relationship between the special Kahler structure data of the Coulomb branch geometry in the global data of the superconformal field theory? Because we know that there are many examples of SCFTs with this so-called kind of global data. And an additional motivation is the following. So this question is particularly interesting for this class of SCFTs because they often have Higgs branch components to their moduli space of vacua, and it's believed that these components can be completely reconstructed from knowledge of what's called the associated vertex operator algebra. And moreover, this VOA is believed to be fully specified by the local data. So it doesn't really, at least as far as I understand it, it doesn't really capture anything you might want to associate with this with global data of the SCFT. And the basic feature of this, which somewhat explains this fact, is or this feature is that the VOA doesn't depend on any marginal couplings. And we know that the marginal coupling, at least for n equals 4 theories, is sort of dependent on the global data. So again, the natural question that results from this sort of motivation is it possible to actually reconstruct the Coulomb branch geometry entirely from SCFT data? So that's kind of what we're getting at. Okay, so the goal of this project is we're going to show the following. We're going to show that the classification of 40 n equals 4 superYang-Mills theories with gauge algebra G is equivalent to the classification of these n equals 4 superYang-Mills special Kahler structures, which are defined by the corresponding Lie algebra G and what's called a principal polarization. And those latter two words will make more sense as we get into things here. And we're going to focus on the 40 n equals 4 theories because they are gauge theories, 40 gauge theories. And we therefore know what field theory data determines their global variance. And this was given to us in this wonderful paper here, which I'll end up referencing a lot, where they show that the global variants are given by the consistent spectra of so-called genuine probe line operators. And furthermore, on the other side of things, the special Kahler structures of these theories are really tightly constrained, and to the point that we can actually classify them and reduce it to sort of a linear algebra problem, which is what we do in this paper, and we go through the whole song and dance there. So yeah, so the specific tasks before us to kind of show this is first we need to classify all the inequivalent special Kahler structures, and then we want to compute a piece of data that's associated with them called their self-duality group. And then we're going to go ahead and compare this with the data that classifies 40 n equals 4 superYang-Mills theories, which are essentially their global variants and the self-duality groups that are associated with the S-duality orbits of these global variants. And later on, I'll remind you of what I mean by the global variants here and how they get kind of organized and acted upon by S-duality, and how you can extract um, uh, what their self-duality group is there. So with that, yeah, a brief outline here. So the next thing we're going to go over is define the special Kahler structures for 40 n equals 2 SCFTs. We'll specialize to n equals 4, and then I will tell you an important sort of mathematical fact that's proven in an appendix of the paper, which essentially proves an equivalence between the special Kahler structures of n equals 4 theories and symplectic integral reps of the Weyl group of the gauge algebra. And then I'll try to describe the sort of algorithm and what our kind of general approaches for computing these inequivalent symplectic reps. And in the process, we'll define what one means by their self-duality group. And then I'll show you the results of this classification, and then we'll go ahead and compare them with the analogous classification of the global variance for the superYang-Mills SCFT. And I'll end with some future directions we'd like to take this in. So let me pause here real quick, get a drink, and if anybody has a question, yeah, feel free to chime in. Okay, let's keep rocking and rolling. Yeah, so an n equals 2 moduli space of vacua. What is this? This is a space that parametrizes the inequivalent ground states of the theory that also preserve n equals 2 SUSY. So you can view the points in this space as being labeled by the vevs of scalar operators, and associated with each smooth point is a low energy effective action that depends on the type of scalar operator actually getting a vev. And we assume that there exists a conformal vacuum, and this implies that the geometries sort of scale invariant, since the dilatations are broken by the vevs, and so that means you have this sort of isometry generated by the action of dilatations. And the inequivalent vacua are going to be labeled by the vevs of the scalar operators in the SCFT. And they can come in two types, and we can distinguish between these based off of the 40 n equals 2 superconformal algebra, which is this guy here, and it's a bosonic subalgebra, where this is just the usual 4D conformal algebra. And then we have a full U2R that we typically decompose into an SU2R and a U1R. And the Higgs branch operators are the operators who, once they get vevs, they're still U1R invariant. And they give rise to the so-called Higgs branch component of the moduli space, which is a singular hyperkähler variety. And then you have the Coulomb branch operators, which when they get vevs, they remain SU2R invariant, and they give rise to this so-called Coulomb branch component, which is a singular special Kahler variety. And there can also exist mixed branch components where you have simultaneously both Higgs branch and Coulomb branch operators getting non-zero vevs. But I'm not going to be talking about either really the Higgs branch or any mixed branch components today. We're just going to focus exclusively on the Coulomb branch. So each of these components, both Higgs and Coulomb, will contain metric, or they have a metric in complex structures associated with them. And each of these structures can experience singularities, but the physical interpretation of what's actually happening at the locations of these singularities is a bit different, or rather like even why they happen. So in the case of metric singularities, they indicate locations where the low energy effective action is breaking down, or in other words, these are locations in the moduli space where we have extra charged states becoming massless. And on the other hand, we also have these complex algebraic singularities, which are locations, at least with respect to the Coulomb branch, where they indicated that the chiral ring defining the OPE among the chiral operators getting vevs in the Coulomb branch is not freely generated, so they satisfy some relations in their OPE. Okay, and now here comes kind of a heavy duty kind of math definition here, and we're gonna sort of break this down into math components and physics components here after I throw this at you. What is a special Kahler structure? So it's basically the structure that is attached to the complex geometry, the Coulomb branch, where this complex geometry is well, on the one hand, some people define it as sort of an integrable system, but geometrically, I prefer kind of viewing it as this complex Lagrangian fibration that has these four pieces of data. So you have this vibration chi, where C star here is a smooth R complex dimensional Kahler manifold. It's the base of this vibration given by pi. And then there's a generic fiber, which, as I mentioned in the first slide there, you can view as a torus, or rather, it's more specifically a polarized abelian variety, which means it comes with something called a polarization J. And then there's also a holomorphic symplectic form omega, with respect to which the fibers are Lagrangian. And so down here is a little kind of schematic of what's going on here. So we have our base given by this C star. There's C star is really just C here with these singular strata removed. But so at the origin here, we have our conformal vacuum. There's, yeah, some singular loci here. And at a generic point, we have a smooth kind of polarized abelian variety where this lambda here, I'm going to repeat this in a moment, but it corresponds to a charge lattice. And when you approach one of these singular loci, the fiber will typically degenerate in some fashion here, indicating that you have some states becoming massless here, some massive charge states whose charges live in the lattice here becoming massless. Okay. So let's break this down. So the key math features are the following. As I mentioned, C star here is the base, the full Coulomb branch modulo the so-called discriminant locus, where these singularities, metric singularities at least, occur. The PAV is specified by a symplectic lattice, which with this J here, the associated symplectic form, which is a non-degenerate antisymmetric bilinear form, and it's integer valued. And it's specified by J here, the polarization is specified by a symplectic basis, where we can assume that it takes this following kind of canonical form, where on the off diagonals we have these R by R matrices, which are diagonal, and they're comprised of these integers di, where each successive di divides the one before it. And yeah, they're positive integers. So when J takes this form, it's in this so-called Smith normal form of the symplectic form. And this pair J and lambda satisfy some compatibility conditions called the Riemann conditions that define the complex torus that AU defines, and they render it sort of a PAV. And when you're in this kind of symplectic basis where these Riemann conditions are defined, AMU has a period matrix, and it takes the following form, and it can be written with respect to this matrix delta here, where these integers are typically called the invariant factors, and then we also have this this other part of the period matrix, which sort of defines the complex structure of the fiber, and it's a symmetric positive definite R bar valued matrix, so it's sort of valued in the R complex dimensional Siegel upper half space. Okay, so what are the key physical features of this? So the polarization J here is essentially what defines the Dirac pairing between both the stable massive BPS states and also potentially any kind of like probe charge states that might correspond to, say, some probe line operators that you want to stick in. And furthermore, the boldface tau here is what represents the electromagnetic coupling matrix um, between this charged matter and the low energy U1R gauge theory that's defined. This sort of defines the low energy effective action at each smooth vacua of the Coulomb branch. Okay, so there are some symmetries that must be kind of that these low energy effective actions possess that must be reflected in the special Kahler structure. The first of which is that the low energy physics is invariant under the EM duality transformations. And these are essentially integer valued GL2R matrices, which are basis changes of the lattice, which also preserve the polarization. And in a compatible symplectic basis, this means that yeah, they leave J invariant and they'll act on this. Oh, apologies. This should be boldface tau. They'll act on boldface tau with the usual kind of Mobius action that uh, um, acts on the Siegel upper half space here. And the set of GO2R matrices that satisfy this condition in a symplectic basis, they form what's called the EM duality group, which is this SP sub J. And an important kind of physical aspect here, really this is kind of the one of the key features of what's going on in the Coulomb branch, is the following. So if we drag this sort of linear system around a closed path, call it gamma, which links some component of the discriminant locus, we're coming back to ourselves. We're on a closed path, so the physics must remain invariant. But this allows the charge lattice to undergo a monodromy, which I'm calling S sub gamma here, where this, because the physics must remain invariant, it must be sort of an element of the EM duality group, which is what I'm saying here. And so what you learn from this is that the monodromies essentially define integral symplectic representations of the fundamental group of C star. And furthermore, we say that if I have two different monodromy representations, they're going to be integrally equivalent if and only if there exists an element of the EM duality group that intertwines them, which is what I'm saying here. And this must be true for all the sort of generators of the fundamental group. So this is the generic story. Okay. So now, yeah, we're gonna specialize to n equals 4 here and see how things will end up sort of simplifying. So yeah, consider we have an n equals 4 superYang-Mills theory. We have some gauge algebra G, and it has its full moduli space is the following flat orbifold, where R here is gonna denote the rank of G, and the gauge algebra has an associated Weyl group. And this Weyl group acts on each factor of C here in what's called the fundamental reflection representation. And so the moduli space, the space of vevs here, this essentially reflects local data of the SCFT that's captured by the Coulomb branch. And at a generic point, the gauge algebra is going to be broken down to some U1 of the R times the Weyl group. And in general, singularities of both types can occur on MG here. And they're gonna, at least the metric singularities will occur at the fixed point loci of C to the 3R under this action of W. But what we can do is, relative to the n equals 4 superconformal algebra, we can sort of pick a n equals 2 superconformal subalgebra of it, and this will allow us to sort of define Higgs and Coulomb branch components of MG. And there's going to be a Higgs branch cut, which contains sort of the same types of algebraic singularities that occur in MG. But on the other hand, the Coulomb branch cut will only contain, it'll only sort of induce the metric singularities. And in particular, the Coulomb branch, it'll take this form here. It'll just be C to the R modulo this complexified action of the Weyl group, where it's still acting on this factor of C to the R and the reflection representation. But topologically, this space, because it's still a flat orbifold, is just C to the R as an algebraic variety, which means that it's freely generated. So the topology here of the Coulomb branches is simple, and there's no algebraic singularities, only metric singularities still occurring at the locations of these fixed loci. Okay. So what we want to do then is classify all the special Kahler structures that can be equipped on top of this orbifold geometry that defines the Coulomb branch for an n equals 4 superYang-Mills theory. Good. So I'm moving a little slow. I'm going to pick it up a little bit. So a special feature of these n equals 4 geometries are that they're so-called isotrivial. This is a really powerful fact, and it means that the polarized abelian variety that's fibered everywhere is actually constant, and it's just given by some model abelian variety I'll just call A. But at every point, instead of sort of the period matrix of AU varying, it's just constant everywhere. So what this implies is, yes, that this period matrix in our boldface tau, this matrix of electromagnetic couplings, is constant. So this implies that the monogamy transformation must actually fix the coupling matrix under the Mobius action. And so this is immediately tells us that boldface tau is going to be in the fixed point set of the action of the monogamy. And furthermore, isotriviality also means that the fundamental group of the Coulomb branch is just isomorphic to the orbifold group in this case, which is just the Weyl group. So therefore, the monogamy map S here defines an integral symplectic representation of the Weyl group into our EM duality group. And we're going to make one more further simplifying assumption, which is we're going to assume that the polarization of the special Kahler structures that we're gonna classify here as principal. And this just means that all the invariant factors are 1, so this matrix delta is just actually the identity matrix, and the EM duality group just becomes the usual kind of symplectic group, defining the corresponding classical Lie algebra. And this is physically well motivated for the following reason. So in this nice paper by Philip Mario Mattoni and Philip's former student Michael Ray, they showed that there's these certain lattices they define called line lattices out on the Coulomb branch of an n equals 4 superYang-Mills theory, and they're in one-to-one correspondence, at least in pure number, not taking into account the action of S-duality or anything, but they're in one-to-one correspondence with the number of global variants, or what's also known as the global forms of the gauge group. And furthermore, they show that these line lattices, they can only serve as the lattice of the PAV if the polarization on A is principal. And so if we want to go ahead and try to capture the global variance of the low energy theory or those at the fixed point here, it sort of stands to reason that we should assume the polarization of our Coulomb branch geometries, and in particular of the PAVs, is principal. One can relax this constraint, and in doing so, you'd effectively, at least according to this sort of interpretation of what a principally polarized lattice here represents, if you were to relax this constraint, you'd effectively be studying the allowed spectra of so-called non-genuine line operators in the Coulomb branch. And this is something that's potentially interesting that we have kind of we're working on in the background. So, okay, with this setup, we're going to start now getting into the actual classification and what's involved here. And the starting point is the following a nice result, which really is what's reducing this this classification problem into one where you can just get your hands dirty with linear algebra and Mathematica, and just start talking about representation theory. So yeah, what is it? We have an n equals 4 special Kahler structure. It has principal polarization, and we have some fixed semi-simple Lie algebra here, corresponding to the gauge algebra of the superYang-Mills theory. And the statement is that this n equals 4 SK structure is an SP2RZ orbit of a pair given by S in boldface tau. And it's an orbit under the action of elements of our EM duality group. And S here is an integral 2R dimensional symplectic representation of the Weyl group into the EM duality group. And it has the property that it's Q equivalent to 2 copies of this reflection representation of the Weyl group. Furthermore, as we previously mentioned, boldface tau here, the coupling matrix is valued in the Siegel upper half space, and it's in the fixed point set of this representation. So what this is telling us is that an n equals 4 special Kahler structure that's associated to a superYang-Mills SCFT is completely determined by this pair up to integral symplectic equivalence generated by the EM duality group. And just maybe want to emphasize that this is really, in general, not true for a generic n equals 2 SCFT. We're really leveraging this result comes about from leveraging both isotriviality and the fact that the base space, the space of vacua here, is an orbifold. Which means that there is a version of this result that also goes through for, say, the n equals 3 SCFTs, which many of which, and perhaps all of them, are also of this orbifold type. So therefore, the task before us is to classify all of these Z reps of the Weyl group. And we also want to classify these the corresponding fixed point sets. So all of these pairs that define these special Kahler structures. So, okay, I'm now going to try to run through this general approach. And I'm going to kind of leave out many details because this is really just one big kind of algebra problem. And there's many pages on details and examples and whatnot in the paper. I'd be happy to talk about any details that might crop up in your head as we go through this at the end. But yeah, I'm just going to kind of try to walk through a general outline of how we went about this in a sort of systematic fashion. So yeah, we have a fixed gauge algebra in principle J. And the first thing we're going to do is construct a canonical form for all possible symplectic Z reps of the Weyl group. And then we're going to compute their intertwiners. And going forward, I'll denote their intertwiners by this math cal M here. So canonical form of S, it's turns out to be the following. So any Z-rep is going to be equivalent to a Z-rep which takes the following sort of block diagonal form in this sort of upper triangular matrix, where let me kind of break down the ingredients here. So these Z-reps are these canonical form Z-reps are labeled by two pieces of data, the first of which is this H, where H here is a subgroup of the center of G. And correspondingly, we have this RH, which is a rank R Z-rep of the Weyl group. And I want to emphasize that this is a rank R Z-rep. It's not a rank 2 R Z-rep, which is what S is. And these guys were already classified, I guess, somewhat recently, back in 1998 by a German mathematician with the last name Veit. And L here is a particular, L sub H here is a particular R by R integer valued matrix, which is called the binding of S. And it turns out that the set of all bindings actually form a group, which I'll denote by math cal B here. And given the fact that we can write everything in this sort of canonical form, one of the things you can sort of immediately deduce just by acting with this form of a Z-rep on a generic boldface tau and working through the algebra that requires tau to be fixed by this 2R guy. What you find is that boldface tau is actually parameterized by a complex parameter, which is not just a generic complex parameter, but actually must have positive imaginary parts. So it's actually valued in the one-dimensional Siegel-Upper half space. And so I'll call this guy the unboldface tau, or tau sub S. And what we'll end up doing is sort of interpreting tau S as parameterizing the conformal manifold of the corresponding SK structure given by the pair. Okay, so the next thing is the intertwiners. And the first thing we'll do is we'll figure out, or this is just how we went about it, but the first thing we did was we figure out what are the intertwiners between these Z-reps taking the canonical form where H is fixed. So the subgroup of the center of the Lie algebra is fixed. And the result is that it's given by a quotient group, which I'm going to call B sub H here, where this quotient group is formed by the group of bindings modulo the group of so-called inner bindings. And I'm not going to explain any of these are kind of some of the details I'm leaving out here, but everything's in the paper, and I actually have some slides at the end if you're really curious. This is just kind of a nice math result, and you can compute this thing in a nice way, doing this sort of X group computations. But this is just the result, and this BH always ends up being at least a product of cyclic groups. So something of the form, Zn cross Zm. It's actually usually even simpler than that. It is just a cyclic group. So what we learned from this, though, is that the inequivalent S's are for fixed H are labeled by some element of this this quotient group, this group of bindings that are not inner. And so I'm going to denote then one of these, go ahead and denote an S here, a Z-rep, by the pair given by a quotient group and an element of the quotient group. And then I'll call I here this math frac I will consist of the full set of these pairs. So it'll contain all the distinct canonical Z reps for fixed H. And so the next thing you have to do is figure out what's the intertwiners between the elements in this set here for basically for different H. So if I'm given two elements of this set, their intertwiners end up being constructed from these maps, which take as input and some 2R by 2R matrix from SL2R and spit out something that's a real matrix, but still symplectic. And they satisfy the following sort of intertwiner relation. And furthermore, they satisfy this sort of compatibility condition. And when gamma is such that the intertwiner is actually integer valued, that means we've found an EM duality transformation that is actually rendering equivalent two of our Z reps here, which is what we're trying to do. And so basically it's the elements of it's the intertwiners that are a part of the EM duality group, which are sort of the low energy duality transformations that relate different special Kahler structures, or rather equivalent special Kahler structures. Okay. So this then allows us to define the so-called duality group of a Z-rep. And the duality group is going to be the set of intertwiners that map a Z-rep back to itself. And so that means it satisfies this equation. And unlike a generic intertwiner, these guys actually form a group. And we find that this is always a subgroup of PSL2Z or a so-called Hecke group, which I'll remind you of what the latter is. Oh, this is a typo. Sorry, you can go ahead and ignore that. But then the action of these self-duality transformations on the Siegel upper half space will generate identifications among boldface tau. Remember, tau was not actually uniquely fixed. It was sort of dependent on this complex parameter. And so the action of the M's that satisfy this equation here will generate identifications within this kind of one complex dimensional subvariety of HR. And analogously, there's also going to be an induced action on this kind of parameter that parametrizes this one-dimensional subvariety. And the induced action is just given by the Mobius action of the 2x2 SL2R matrix parametrizing the self-duality transformation. And once you take into account these induced identifications on tau here, this is sort of what we'll end up defining to be the quote-unquote conformal manifold of the special Kahler structure given by A. And geometrically, this conformal manifold has the geometry of the modular curve formed by the self-duality group of A. So it's going to be effectively the Siegel upper half space modulo the self-duality group of A. Okay. So these self-duality groups, I didn't give them a name on the last slide, but and sorry again, this is should be L. Oh man, this is full of typos here. But these self-duality groups, they only had to be valued in well, actually SL2Q, even though generically they could be in SL2R. But yeah, what we find is that for the simply laced case, they can always be expressed as subgroups of SL2Z. And for the non-simply laced case, they end up being subgroups of the Hecke group. So they actually, some of them are SL2R valued. But for simply laced G, the relevant subgroups of SL2Z are the following. So you have the two types of congruent subgroups, and then this sort of real one, which we end up also calling delta. And they're just given by SL2Z matrices that satisfy these relations. These are sort of their defining relations. So, and among those that actually appear as self-duality groups, they have an index with respect to PSL2Z or SL2Z, which is given in the following table here. And yeah, this just might be good background data to recall when we compare with reading between the lines. Okay, so here are the results then. I'll present these in two parts, starting with the simply laced case and the non-simply laced. But yeah, so what should you pay attention to here? In the second column, we have each row corresponds to an SK structure orbit, and the pairs in the orbit are the SK structures for a given H. And so this is like, for example, or let's just take the SU R plus one case as the example, but for every square divisor of R plus one, you get an SK structure orbit, and where each one of those SK structure orbits is labeled by this quotient group and then an element of the quotient group. And so that's what the labeling sort of means here. And everything that's in a bracket is equivalent. So there exists a sort of EM duality transformation relating the corresponding Z reps. And when we have these sort of teal arrows here, that's telling you that you have sets of Z reps which are related not by the standard equivalence relation that I showed before, the standard intertwiner relation, but it's actually an intertwiner relation that's also composed with what's called a reflection-preserving outer automorphism of the vowel group. This is sort of a subtle detail slash complication. I'm not going to really talk about it anymore, but it is kind of reflected in the table here. And so whenever you see something in this teal color, it's sort of is telling you that there's a relation or an equivalence relation that's being generated from one of these more general kind of equivalence relations between Z reps. Okay, and the last thing is we have some red X's everywhere, and these are where we end up having disagreements between the global variance classification. And yeah, I'll say a little bit more about those once I show you the latter classification. Yeah, so any questions about this table here? All right. Okay, so then before showing you the non-simply laced case, let me remind you of what these Hecke groups are. So at least for the sort of relative theory, the way these guys come about, and where by relative theory I mean just the superYang-Mills theory as with no global structure kind of chosen. So it's just given by the gauge algebra and the corresponding marginal coupling, tau Yang-Mills, which has nothing to do with the other unbold-faced tau that you've seen a couple times. And so, yeah, these Hecke groups, they're labeled by a number Q, which itself is labeled by this script L, just called the lacing number. But these are subgroups of PSL2R. they're still generated by two elements, a sort of SL transformation and the usual T transformation. And they act on this equal upper half space via the kind of standard Mobius action. And the relevant cases are when Q is equal to 4 or 6. And it turns out that it's the BCR cases that in F4, which have the S-duality group is this H4 Hecke group, and for G2, it's H6. And somewhat sort of curiously is the following fact, which is that all the index n-congruent subgroups of PSL2Z also end up being finite index subgroups of these Hecke groups, although the index with respect to the Hecke group might be different. So for example, here we have gamma 02. This is an index 3 subgroup of PSL2Z, whereas it's only an index 2 subgroup of H4. And among those that actually appear as self-duality groups, not only for us, but in the case of the global variance, they have the following index with respect to H4 and H6. And just to complete the picture here for gamma 04, this is actually index 6 with respect to PSL2Z. Okay, so here's the results for non-simply laced G. Yeah, it's a bit of a simpler picture, but one of the things to point out is that at least in the BC2 case, it's somewhat interesting that we have two different SK structure orbits given by these two rows, and there's an outer automorphism, which is a self-duality transformation of this orbit, and there's also an outer intertwiner that actually relates two different SK orbits. And likewise, the same thing is happening down here. Okay. So now we want to go ahead and compare these results with the classification of 40 n equals 4 superYang-Mills theories. And yeah, this essentially is done by or comes from the classification of the global variance of the 40 conformal gauge theory, which is we're going to kind of go through this real quick, and I'll remind you of what those results are. But basically, in this reference here, which I'm just going to call RBTL from now on, corresponding to the title of the paper reading between the lines, they computed the S-duality orbits of the global variance, and from these orbits, you can deduce what their corresponding self-duality groups are. And this is effectively equivalent to classifying what you might call the moduli space of the relative n equals 4 superYang-Mills theory that's just given by the pair that defines the kind of local data of the conformal gauge theory. And whereby moduli space here, what I kind of really mean is what I would call the connected sum of the conformal manifolds for the distinct global variance of the relative theory. Okay, so yeah, what are the global variants of a 40 gauge theory? So if we have a simple gauge algebra G, the global variants are labeled by the consistent sets of probe, Wilson, and 't Hooft line operators. And these sets, they're called the global variants. And they turn out to be in one-to-one correspondence with the global forms of the gauge group. Plus, you have to define a value for these so-called discrete theta angles. But we label the latter I'll denote the latter in the following way, where I have some G, where G here is just going to be the gauge group specified by the simply connected, the unique simply connected group corresponding to the gauge algebra modulo some subgroup of the center. And this I here is just a label, discrete label that labels one of these discrete theta angles. And S-duality, it acts on these the GI, and it organizes them into some S-duality orbits. And the set of the S-duality transformations that actually fix the global form, fix the global variant, is called the self-duality group. That's kind of what I'll define to be the self-duality group of that global variant. And every global variant that's in the same S-duality orbit, they will necessarily have the same self-duality group. And furthermore, each S-duality orbit then has an associated conformal manifold, which is going to be given by the modular curve formed from the self-duality group of the global variants that it comprises, that are sort of related by S-duality transformations. Okay. And so here's the sort of first non-trivial example where non-trivial means I have more than one orbit occurring. So this is the case of where we have G is equal to SU4, and these are the various GIs here. Yeah, we have the arrows which denote the S-duality group in this case is just SL2Z, which, as we know, is generated by these S and T transformations, and so they sort of act on the various global forms in the following way. The result is that we have two orbits where this guy here forms a single orbit by himself, and the other six global forms. Oops, that's what I should do. The other six global forms form the other orbit, and the self-duality group of the six-element orbit is gamma 04, which is index 6 with respect to PSL2Z, and then there's this other one which just has a single global form, and its self-duality group is just the full PSL2Z. So, okay, here's the results then for the classification of the global variants. Again, in the second column here, we have each row labels a global variant sort of orbit. And anything in red is just identifying where the mismatch occurs among this classification relative to where all the red X's occurred in the previous tables here. So anywhere where you see a red X, or sorry, red here, there's a corresponding red X occurring in the SK structure classification table. Okay, and then we also have the global variance for non-simple G. And again, you're probably all quite familiar with this. So what's actually most interesting is the explicit comparison. So first, before I just mention and go through the comparison, make some targeted comments, just two remarks. So first, relative to our sort of special Kahler classification results, we can really only compare two pieces of data with this RBTL data. And that's, we can compare the number of equivalence classes, i.e. the number of S-duality orbits of global variants, or the number of EM duality orbits of Z-reps. And we can compare what the self-duality group of each of those respective orbit types is. And the reason for this is because it's really, these are the two pieces of data that are sort of gauge invariant on the conformal manifold of either the SCFT or well, really, yeah, it's really the gauge invariant data of the on the conformal manifold of the SCFT, by which I mean this is sort of the data that doesn't depend on where I'm at on the conformal manifold, meaning it doesn't matter if I'm close to weak coupling. These quantities sort of stay the same. But one of the things it sort of implies is that we can't compare the number of quote unquote global forms of the gauge group in an SK structure orbit. as one can do, and as they did in the reading between the lines paper. Um, in other words, there's really just no intrinsic analog or no mapping from an SK structure given by this pair, or rather its corresponding Z-rep, and a global form of the gauge group, one of these GIs. It's just the classifications just don't kind of line up in that way. So okay, so what are the discrepancies that occur here, where all those red X's occurred? So they came in two types, and one was either a disagreement in terms of the self-duality group, or a disagreement in the number of orbits. So the self-duality disagreements, they occurred for the A1 case and the BCR case, and for the D4K+2 case. And in the former two, the A1 and the BCR cases, the discrepancy was there's always a single SK structure orbit that has a self-duality group, which is PSL2Z, when according to RBTL, it should be gamma 02. And for the D4K+2, there was a single SK structure orbit that had self-duality group, this gamma 02 congruent subgroup, when it should have been the gamma 04. And this one we sort of know why this one occurs, or this discrepancy occurs, and it's because there is one of these, there is a self-intertwiner coming from one of these reflection-preserving outer automorphisms of the Weyl group, and these are sort of, at least in this case, it corresponds to the outer automorphism of the Lie algebra D4K+2, and this just like wasn't kind of taken into account in the RBTL paper. But here we take it into account, and so that's why this discrepancy occurs, and you sort of see a self-duality group that's too large. And for the second type of discrepancies in terms of number of orbits, this occurs for all the D4K cases. And there we find that there are just additional equivalences that are generated by these reflection-preserving outer automorphisms. That again, these just aren't taken into account in the RBTL. But they sort of come from the outer automorphism of the SO even Lie algebras that relate the spinor and co-spinor. That's precisely what these outer automorphisms are. Okay. So that's it. So yeah, wrap up and mention some future directions here. So one thing that we can readily do, as I think I mentioned, is that we can extend these results to 40n=3 SCFTs, because their space of vacua, their orbifold geometries, and they're isotrivial. And things are actually a bit easier in this case because there's no self-duality groups involved, or because there's no conformal manifolds for these theories. And this is something it's a work in progress, but we do have some like interesting sort of preliminary results. And one of the interesting features is that it looks like some n=3 theories don't admit special Kahler structures with principal polarization, which are precisely the ones that will be classified here in the case of n=4. And so it's a bit of an open question as to what this means physically. And according to the interpretation that's motivated by the results I just went through, it might mean that these are actually SCFTs, which are inherently relative, meaning there's no sort of absolute version of them. They don't have any kind of global data that completes them into an absolute theory. A question, though, is if we can go ahead and do this analysis for the n=3 theories, and then we'd like to confirm the results using a corresponding symmetry topological field theory. This is also something we're thinking about. And And as I also mentioned at one point previously, we can go ahead and try to classify non-principally polarized special Kahler structures corresponding to these sort of non-genuine line lattices, if you will. Um, and then sort of a bit of a broader question is if we can extend some of these methods to perhaps orbifold n equals 2 theories that are not isotrivial, although I don't think we even know of any examples of this type. Um, but you also might ask the opposite question, which is, can we extend these results to n equals 2 theories that are isotrivial, but perhaps not orbifolds? And that one actually might be possible. We're kind of thinking about it. Um, and in sort of a different direction, one thing we'd like to know, understand a bit better is how some more features of generalized symmetries are encoded in the moduli space. And in particular, we'd like to know uh, how we can see one form or the two form slash zero form symmetries that are present in n equals 4 theories, or also we know that you can construct these sort of non-invertible duality defects when you do have an SCFT with a conformal manifold with some duality groups. Um, and furthermore, given that we can identify these generalized symmetries in terms of moduli space geometry, we'd like to know what it means to sort of gauge them and also detect their anomalies or potentially any higher group structures, something like this. And lastly, we still have this sort of lingering kind of long-term question that we're chasing here, which is how much SCFT data can be extracted from the moduli spaces of SQFTs. Um, yeah, so plenty of fun stuff to still be done. But with that, yeah, I'm a little over time here, so I apologize, but that's it. And yeah, I'd be happy to answer any questions or yeah, comments
All
or
right. So let's
clarify.
thank Mitch. And do we have questions?
Yeah.
Hello. Yeah, very nice talk. Can I ask some stupid question
Sure.
maybe?
Yeah,
Uh,
absolutely.
can you go back to the page like when you're trying to embed the Weyl group inside the SP 2R? Yeah,
Yeah. How
it's
far
quite
back?
early on.
How far back is this? Like pretty far?
Yeah. I think it's at around page 5 or page 6. Not remembering exactly. So when you define the map S and you send WG into SP2R,
Uh-huh.
still early on, I guess.
So S here.
Where is this? Oh no, it should be later. Let me check.
Yeah, this is where S gets
Probably
initially
around
defined.
here. Yes. And then you have a map of S sending omega G instead WG instead SP2R.
Yeah, this is where it's initially defined.
Uh,
And then maybe you're talking about a little later on when
yes. Uh,
around here. Yeah.
roughly.
So here's
Yeah, so my question is like how many of this WG inside SP is gives you a simple yeah, here.
here we go.
Exactly.
The definition of
Yeah.
the SK structure. Yeah.
So 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 how many S will give you a symplectic reflection? Do you know this?
Oh, yeah. So in general, um, this depends on really. I mean, given we have this canonical form. So if you were to give me any of these symplectic Z reps of the vowel group, these 2R dimensional ones that uh, yeah, so any of these, I know I can always conjugate it into something of this in this canonical form. And the statement is that for some H here and
Mm,
also for some binding. But the space of bindings here of these L's is essentially infinite.
mm.
Um, so there's count yeah.
So only for special cases, the symplectic reflection, you will see.
Yeah, yeah. L takes a specific form, which I didn't give here, but you can write it in terms of this some other symmetric matrix, and also in terms of these rank R Z reps of the Val group.
Mhm.
But yeah.
Yeah, I can see when if LH this part is trivial, then it's definitely a symplectic reflection. But yeah, maybe LH. Yes. And another question is like if you want to do it for 14 to 3, you just replace this Weyl group into any complex reflection group, right? And you do the simulus analysis.
Yeah, that's right.
Is there
Uh,
anything more other than this process?
no, this is basically you'd have to go about it doing a similar uh, sort of algorithm here, but it would also it can't just be a CRG. It'd actually have to be a CCRG, meaning it had to be a crystallographic
Mm-hmm.
complex collection group, probably because it has to act on the lattice of the fiber and
Yes.
preserve it. So you do need to be able to have the CRGs that for which such lattices exist.
Mm-hmm.
But yeah, that's the kind of a name of the game there.
I see.
And
I
like I
see.
said, you just wouldn't have any of this um, conformal manifold sort of structure that you could associate with um, the fixed point set of the corresponding period matrix. Like in that case, for the CCRGs that are not Val groups, um, boldface tau here, the coupling matrix would actually just be fixed. It wouldn't form this sort of 1D subvariety of HR.
Mm-hmm. I see. So, is this like the full? Is there any other like how you call it, crystallographical group other than the Weyl group and the complex reflection group?
Um,
So, like you took a random subgroup of this SP to add that, which is crystallographical. Are they necessarily falls into this class or?
I'm not sure. As far as I know, those are the types of essentially orbifold groups uh, you can have when you're working under the assumption of having a freely generated Coulomb branch.
Mm,
When you make that assumption, that sort of tells you that the orbifold group must be at least a CRG, because this comes from this Chevalley-Shepard-Todd theorem, which essentially says
yes.
that if it's freely generated, then it's going to be an orbifold by a CRG. Um, yeah, but so if you want to move away from that and go ahead and consider some isotrivial geometries,
Mhm.
consider those that have complex singularities, maybe you could get away from this
Mm,
sort of class of orbifold type theories and get something more general. There actually might be some examples of such cases in a paper by Philip, Mario, and Antoine from like 2019, where they talk about stuff like this triple special Kahler structure, defining the sort of special Kahler structure, the n equals 3 version of a special Kahler structure for n equals 3 moduli
mm,
space. So
I see.
yeah.
Yeah. Thank you.
All right. You have more questions? Well, if not, then I'd say let's thank Mitch again,
Awesome. Yeah.
and we can go off the record.